Today is Module 3. For those just joining, my name is Jean-Claude. We'll be looking at the design objectives. Objectives for this module: the hierarchical network models, the network blocks, and we'll define the design objectives. This is a CCDA class. It's about Cisco's exam, so this will be the Cisco's 5 design objectives. Cisco's 5 design objectives. Well, what are they? Well, first one would be hierarchy. We'll come back throughout the module 3 and 4 about this hierarchy. Modularity. We'll go deep into the modularity. Scalability. This will lead us into resiliency, and then the fault domains. We'll define each of them. We'll explore each of them. Today, probably when we'll go through modularity, we'll do some part of a later module which is about enterprise campus. So we'll be deviating just a little bit so that this module makes sense and that is meaningful to you. And then we'll come back in. Sometimes we might skip a little bit forward in scalability and come back into modularity or resilience and come back. Then again, this is a design class. We'll be looking at technology placements. We're not going to do any configuration per se. So the hierarchical network design models. Well, Cisco says a hierarchical network design model breaks the complex problem of network design into smaller, more manageable problems. Each level or tier in the hierarchy addresses a different set of problems. This helps the designer optimize network hardware and software to perform specific roles. So yes, if we had a flat, giant layer 2 network and we have a layer 2 problem, well, it's a huge block to troubleshoot. Now, if we manage to make different tiers and use different technologies, well, we kind of create boundaries to those technologies. We'll come back to that later, but it makes it more manageable. So that's why Cisco go ahead with this hierarchy model. So what are the benefits of the hierarchy models? I mean, if we're going to invest time learning about it, there might as well be some benefits to it. Well, the first one is lower capex. Well, what we call the capital expenditure. So let's say you're an architect, you're presenting this to an outside or an inside customer. Well, one of the first few things you'll learn is that budget toward the capex is kind of important. So if you present a network design and you can show that your hierarchical model, the way you build it, is going to lower their capex than just flat out buying stuff as you go, well, you have a point there. It's easier to understand. Usually when we build a network in a hierarchical manner, we'll have a north and south that is very easy to identify, and so that even someone that is not fluent in networking will be able to make sense of it. Also, another benefit is easy network growth. So we'll see later with modularity how you can scale out or scale up a network, and also better fault isolation. Hierarchy. Well, if we look at this design, we have 3 blocks here. But even though we have only 3 blocks, we have a couple of devices. The first block, the one on top, is called the core. Your core is your centralized gateway to other parts of your network. This should be hosting your fastest and meanest hardware. This is where the traffic must flow as fast as possible. Then we have the distribution. Most people call it the aggregation block. This is where you aggregate all the connection going south, or if your distribution is one going toward your WAN, that would be aggregating your network flow going north toward your access and the access layer. We'll come back into defining each of those blocks, but as you can see, the more you go south, the more you go down from the core to the distribution to the access, the more devices you're going to see. And as you can see, because we have more devices here, we'll need faster hardware here because we're actually aggregating the traffic of all the network, all the access. So what about the core? Well, the core, like I said, should have very fast transport, should be highly reliable. When we looked at the previous slide, we said that there are a lot of devices connected to the core. Now, if your core go down, might as well just say that you lost most of your traffic. So it has to be highly reliable. It has to be redundant, so you need more than one device. You don't want your single point of failure to be your core. It has to be fault tolerant. We'll see later. There's some technologies we can use to make it fault tolerant. Low latency. This is another key point. You don't want this hop to add latency because everything will go through your core, and sometimes I go twice through the core. So if you're reaching a service that's far away from the access block, well, you have to go through the core to reach it, and he'll have to go through the core to come back to you again. So if you have a high latency core, well, this adds up. You need to avoid any CPU intensive packet manipulation. So any complicated access lists, any deep inspection of the packets. You shouldn't do any inspection like let's say you want to do inspection IPS of run a inspection packet service at this level. I don't think that's a good thing. Like I said, it's aggregating everything in your network. So imagine the device within the core will be the busiest one forwarding the traffics. It has to have consistent diameter. We'll come back to this. And you have to maintain QoS. If you go from an access block to a service block and your core is not maintaining QoS, it means you're not having QoS end to end. You're just having QoS between let's say your access and your distribution. Diameter, well, it's referred to the number of device a packet of frame crosses over. At layer 3, this would translate into hops. So at layer 3, it's pretty easy to figure out. 5 hops will be a diameter of 5. At layer 2, this would relate to your spanning tree distance or delay of convergence propagation. So if you have aggregation of switches to another switch at layer 2, well, this grows your diameter of your spanning tree. Let's have a look. A layer 2 diameter example. So on top we have our core switches, and then we have the aggregation switches, and we have the access block, so the access switches, and we have multiple hosts here. So this would be our first diameter. So let's assume this whole environment is a flat layer 2 environment. Just for the sake of an argument, we would never do that, but let's just say. It means this would be the first diameter. So if this switch here creates a reconvergency event, it will be propagated to this guy here. Now, if we create another diameter, it means anything that happens here will be propagated into the other block, and so on. And same thing here, we would have a diameter of 3. So you can look at it this way. If I have an event here that is going to propagate, the time it takes to reach this one and this one and back to another one to another one. So this is your diameter. Actually, yes, for those that just finished their CCNA, you'll see that with the timing of the spanning tree, this could create an issue. Furthermore, look at this one, this little guy here. See, this little guy is outside of the first diameter of 3. Now, if we include this little guy here, that's a diameter of 4. So we're not consistent across all our network devices here. So previously, when we said the diameter must be the same, it must retain. So this little guy here should be moved into the next one. I know it's looking at this network diagram, it seems very obvious, but when you go to a customer's place, that kind of setup, we see that often is when they grow internally. So they have this third floor, they have a nice closet switches, they have multiple switches, and then for some reason a department on that floor deployed a small contingency of servers, or maybe they outgrow their closet, so they hired more people than previously expected, and when they add another switch, they just trunk it to the last switch that's in the closet, thus creating another diameter in your network. A layer 3 diameter example, well, let's assume our layer 3, these devices are layer 3 and these devices are layer 3. And look at this link. This link here will create our inconsistent diameter. So if network from this computer travels to this one, it'll go through 1, 2, 3, 4 hops to reach the next host. Now, if for some reason you remove the link up here and leave this link here, one of the potential issues, or if your link between your aggregation and your core are of unequal bandwidth, you could end up with a situation like this, going through 1, 2, 3, 4, 5, 6, and then back to your host. So this would be another example of a diameter that's unequal. So when you connect your core to your distribution, and that we saw previously in the slide, it's very important that the links going to your core are of equal bandwidth, so that you don't end up with a different diameter size. It needs to remain constant. The hierarchy. Now at the distribution, let's define the distribution. The distribution will be your policy-based connectivity. So if an incoming traffic from your access needs to leave a certain port toward the core, this is where you would define it, not at the core. You don't don't define the incoming port of your switches at the core. You define the outgoing port on your distribution. It is very important because the distribution has a lower it's less active. Not all the network flows will go through the distribution of each part of your network, contrary to your core. Redundancy and load balancing, this would be the place where we do it at the distribution. Load balancing, we'll see it through some protocols. That's how we'll do it. And redundancy, mainly from your access. So we'll look at redundancy of links. The links toward the core needs to be redundant. Also, the devices themselves. We'll see that later. From the access block. So if you have more than one distribution, it's kind of important. We don't want to create any single point of failure between the access and the core itself. We aggregate the access block. So on the first slide, we saw many access switches. These needs to be aggregated at the distribution block. We don't aggregate at the core necessarily. And if we do, we'll see that later. We're going toward another kind of design. Normally this is driven by budget. So most of the time what happens is that your customer is willing to renew, is willing to implement this nice new network of yours, but the budget will allow you for the perfect solution. So we need to do some compromises. So in that case, we can collapse the core and the distribution together. We call it a collapse distribution, collapse core. But at the core, we will be aggregating the access switches from the access block, and we can also aggregate the WAN connection. In a perfect situation, you would have more switches to aggregate your WAN. Quality of service needs to be implemented at this layer, and security. Now, this is where you could or should do your deep inspection, apply stringent rules, create firewalls if you want to. Also, this would be where we create different layer 3 areas. Let's talk briefly about OSPF. This would be a great place to create an OSPF area so that it is summarized. See, we say summarization, so that you could summarize your area toward the core. The core could be your backbone, your area 0, and have all these distribution blocks using different areas if you wanted to. Summarization, yes, we do it at the distribution block. If you're using EIGRP, for example, this would be a nice, very nice place to summarize all your VLANs subnets. And at the same time, we do the inter-VLAN routing. And if you look at your access distribution core, and then let's go toward our WAN. Then would be another block of distribution, and our edge or access on top. Well, same thing. We'll be summarizing. For example, you will not redistribute the whole internet routing table within your network. You would summarize at that point. So the distribution is a great place to do it. Inter-VLAN routing, yes, definitely. If you have east-west traffics, and when I say east-west traffic, not necessarily layer 2 east-west, but inter-VLAN, so a subnet toward another subnet, so two departments that needs to be reachable internally. So this is where you would do. So this would alleviate some of the traffic going through your core. Redistribution, especially from your WAN, you would normally redistribute over there. So sometimes in design we prefer to use an internal gateway routing protocol and use an external on the head-end routers. We'll come back to defining these. Like I said, we'll be jumping forward and back, but this would be a great place to redistribute between protocols. Demarcations of your layer 2 to your layer 3 also. I've seen some designs where the demarcation is at the access block. Yes, it's doable. It's a bit more expensive because instead of scaling at layer 2 with cheaper layer 2 switches, you're actually scaling with multi-layer switches or layer 3 switches that has layer 3 capacity, and those are a bit more expensive. This is also where we receive normally, or we do the dynamic and the static routing protocols. We do it at the distribution, and this is where we define our broadcast and multicast domain. So through the use of VLANs, you can contain your broadcast domains, and also through IGMP groups, you could also contain your multicast domain. So a bit more in the enterprise network design. Like I said, we'll be doing some of the content that we should see later. So let's say we do our layer 2 and layer 3 demarcation at the distribution block here. So going from this switch upward will be, or northbound will be layer 3, and southbound will be layer 2. Doing so, we create two separated broadcast domain. So the domain on the left is isolated from the domain on the right, because northbound of my distribution block, we're running layer 3. Now, at the access, what do we need? Well, normally we run layer 2. And one of the key points is high availability to hosts. So the access block should be highly available. Now I say to hosts, but especially to servers. I've seen some pretty hefty access switches with multiple modules, so that within a switch we have redundancy, or if you have, normally you have a server with multiple Ethernet ports, well, you would connect to multiple access devices. Port security, well, more on this in the CCDP classes, but this is where you would implement it. Broadcast control, and when I say broadcast control, I'm not referring to defining a broadcast domain at the distribution, but controlling your broadcasts. I don't remember if it's part of the CCNA or CCNP, but normally there's some configurations, commands you learn on the port level that you can apply a storm control. So this is where you would do it, and this is where you would mark and create trust boundaries for your QoS. Line rate limits, yes, you can impose a limit on the port. This is where you would do it. And policing, well, you could even make it so that it drops the traffic. This could be toward a threshold, could be toward a destination. ARP inspection and VACLs. VACLs. I'm pretty sure you guys will see it in the CCNP, and for those coming back from the CCIE, this is no new for you. VLAN access control list. Also the spanning tree. This is where you'll be using spanning tree because it's a layer 2 domain. Power over Ethernet considerations, yes, that's you should do it from the access. Private VLANs and many other security considerations and services.